Okay, on to section 6, verifying that the point lies on a line. So this is our first question involving the vector equation of a line. Okay, this is often appears as r. What it says in your notes is that r equals a plus a parameter, which we often use this letter lambda for, times a d, and that this is a position vector, and that this is a direction vector. So that's a theory you need to know of lines, okay? But in fact, you don't actually need to apply that to this particular line. You just need to know what this lambda is all about. We call it a parameter. The job of this lambda is to generate different values of r. And by r, we just mean the position vector of the point we're trying to describe. So that's just x, y, z. So you can always change r into x, y, z, okay? Maybe it looks a little bit friendlier. So in order for this point to lie on this line, it must be that it's possible to get x, y, z equal to 4 minus 1, 2 by choosing the correct value of lambda. So all I need to do is think what value of lambda would work. And if it works for x, it's also got to have to work with the same value for y and z. I can just look at the x ones to work out what lambda would have to be. So you don't actually have to write this bit down. What I'm thinking about is what value would make x work. So for x to work, I would need this x here, this 4 from the p, 4 would have to equal 7 plus 3 lambda. I'm just looking at the x bits. X equals 7 plus 3 lambda. And that means that solving this easy equation for lambda, 3 lambda would have to be minus 4, so lambda would have to equal minus 1. Okay, so that is just me getting the value of lambda. That is actually something that you wouldn't have to write down, well, apart from this bit, okay? When lambda equals minus 1, and that could be the first thing you write down, okay? If I can invent a value of lambda and show that I get the right point, then I've finished. So when lambda is minus 1, x, y, z, sometimes called r, you can use r or x, y, z for this, equals, okay, this bit which is always the same, 7 minus 3, 3. But I reckon that the clever thing here to use for lambda is to plug in lambda is minus 1. So minus 1 lot of 3 minus 2, 1. If this is going to work, then when I do this calculation, I should get the point I wanted. Okay, which I must do, otherwise the question was lying. So 7 take away 1 times 3 is 4. Well, that was always going to work because I made that happen. Now, 3 take away 1 times minus 2. Well, minus 1 times minus 2 is plus 2. Minus 3 plus 1 is minus 1. Okay? And for the last one, I've got 3 take away 1 times 1 is 1. So 3 take away 1 is 2. So the vector I've got is 4 minus 1, 2. But that is exactly the vector OP. It has to be. Okay, I've generated the position vector of this point by choosing a suitable value of lambda here. Okay, so the value of lambda that made the x work out also made y and z work out. So to show that a point is on a line, all you have to do is come up with a value of lambda that when you lob it into the equation of the line does actually give you that point, which is what's happened here. But I haven't finished. It's a verify, so that's a kind of, it's not quite the same as show that, because I'm allowed to start with the equation of the line and just check a value of lambda works, but I've got to state my conclusion, okay? So therefore I have to say P is on the line, okay? And they're looking for that explanation for you to get 4 marks.